Hello everyone, I'm Lokesh Anand Ramadasan, a student at California State University, Fresno. I'm thrilled to present my research on C-wave direction using the name-based algorithm. This topic is particularly interesting to me due to its significant implications for coastal management, shipping, and marine renewable energy. Now, let me walk you through what we will be discussing today. These are my contents for this presentation. Our presentation will start with an introduction to the topic and some background information on C-wave detection. We will then move into the classification of C waves. Following this, we will explore the naive-Bayes algorithm and its implementation in our context. We will discuss the challenges faced during this process and present our proposed solution. Next, we will analyze the outcomes of our approach and present some data metrics to evaluate our performance. Finally, we will wrap up with a summary and conclusion of our work. Let's begin with the introduction. CO detection holds immense importance for various sectors. Firstly, for coastal management, understanding wave patterns is critical for planning and preventing coastal erosion. Secondly, in the shipping industry, accurate wave detection can aid in safer and more efficient navigation. Lastly, in the field of marine renewable energy, wave detection is pivotal for harnessing wave power efficiently. In older days, sea wave detection has been achieved through various methods such as buoys, radar, satellites, and computer models. These methods, while effective to a certain extent, can be cost intensive, require significant maintenance, and can also be susceptible to errors due to environmental factors. We propose the use of machine learning algorithms, specifically the naive-Bayes algorithm for sea wave detection. Machine learning can offer increased accuracy, efficiency, and cost effectiveness in detecting and classifying sea waves. Now, let's dive deeper into the background of sea wave detection. Sea wave detection involves identifying the presence, characteristics, and movement of sea waves. This is achieved through a variety of sensors and techniques, including radar, buoys, satellites, and computer models. The significance of sea wave detection is manifold. It plays a pivotal role in weather forecasting and oceanography, providing valuable data for predicting weather conditions and understanding ocean currents. In maritime safety, accurate wave detection can warn against potential threats such as tsunamis and cyclones, thus safeguarding lives and properties. In the offshore industry, it helps in optimizing operations, thereby reducing costs and risks associated with adverse sea conditions. Furthermore, in the realm of shipping, sea wave detection aids in efficient ship routing and navigation by predicting sea conditions. Ships can alter their routes to avoid dangerous waves, thereby reducing fuel consumption, minimizing costs, and decreasing the risk of accidents at sea. Thus, the importance of accurate and efficient sea wave detection cannot be understood. Let's now understand the sea waves, how the sea waves are classified. The classification is primarily based on their heights. The first type is normal ocean waves, which usually range from 1 to 3 meters in height. However, during storms, these waves can reach up to a maximum of 6 meters. The second type is rogue waves. These are considerably larger, reaching heights of 20 meters or more. While they are rare, their sudden occurrence can pose significant threats, causing substantial damage to ships and offshore structures. The third and the most destructive type is tsunamis. These massive waves can exceed heights of 30 meters and are usually caused by underwater earthquakes, volcanic eruptions, or landslides. They can travel across oceans at high speeds, causing widespread devastation upon reaching coastal areas. We have chosen to focus on the naive-Bayes algorithm for this study, and let me explain why. The naive-Bayes algorithm is a probabilistic classifier based on Bayes' theorem, which calculates the probability of an event A given to event B, as we have mentioned in the presentation. One of the key assumptions of this algorithm is that the features are independent of each other, making it naive. Despite its simplicity, it is highly effective for classification tasks, including our goal of classifying different types of sea waves. The advantages of using the naive-Bayes algorithm include its simplicity, making it easy to implement and understand it. It's also efficient, capable of handling large datasets quickly. Finally, it's robust to irrelevant features, which means it can maintain performance even when some of the input features are not relevant to the output. Now, let's discuss the implementation process of the naive-Bayes algorithm for C-wave detection. There are 5 key steps involved. First is data collection, where we gather a dataset of C-wave patterns. This dataset would include features like wave heights, frequencies, and velocities. The second step is data pre-processing. Here, we clean and normalize the data, preparing it for the model. Next, we have feature extraction. This involves selecting the most relevant features from our dataset that would help in accurately classifying the wave types. The fourth step is model training. Here, we input our pre-processed data into the naive-Bayes algorithm, allowing it to learn and create a model that can predict the wave type based on the features. The final step is model testing. We test the trained model on a separate set of data to evaluate its performance and accuracy in classifying sea waves. Any fine-tuning needed would be done based on the testing results. In our journey towards sea wave detection, we encounter challenges both from traditional methods and machine learning implementation. Traditional methods pose issues with high-cost complex systems and environmental susceptibility. Meanwhile, employing machine learning algorithms bring challenges in data pre-processing, feature extraction, and algorithm selection. Our proposed solution leverages the naive-Bayes algorithm for C-wave detection. The process involves adapting the algorithm using feature extraction to simplify data and conducting rigorous training and testing with a dataset of C-wave patterns. This approach aims to create a more efficient and reliable tool for C-wave detection. This is the outcome of the C-wave detected using naive-Bayes algorithm. Here, this chart demonstrates how the naive-Bayes algorithm successfully categorizes C waves based on their heights. Over time, it distinguishes between normal waves, rogue waves, and tsunamis, showing its capacity for C wave detection applications. Our data metrics indicate the naive-Bayes algorithm performs effectively in C-wave detection with high percentages in accuracy, precision, recall, and F1 score. These measurements suggest the algorithm's promising performance in classifying different types of C waves. In conclusion, the naive-Bayes algorithm presents a promising solution for C-wave detection. It overcomes traditional method challenges and with further refinement could significantly contribute to maritime safety, coastal management, and renewable energy applications. Thank you for your time and attention. I hope this presentation has shed light on the potential of the naive-Bayes algorithm in C-wave detection.